Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. Now we're going to look at a heterogeneous bubble nucleation system in a weightless environment. And this is a fancy way of saying that we're going to see the salvation to future space colonists heartburn, zero gravity heartburn, because what we have here is an effervescent antacid tablet. And we're going to see what happens when this effervescent antacid tablet is introduced into a sphere of water.
To generate bubbles, you can have bubbles form from solution, like when you open a bottle of soda pop and the gas that has already been dissolved in solution is just coming out, and that's a homogeneous nucleation problem where the bubbles spontaneously form in the center of the liquid. Here we're going to look at heterogeneous nucleation, where we have a solid, which in this case is a effervescent antacid tablet, and this will be added to this 50 millimeter diameter sphere of water, where the water will chemically react with the effervescent antacid tablet and produce bubbles of carbon dioxide gas. And these bubbles will form on the surface of the antacid tablet, and that presents a heterogeneous system where the bubbles can be popped off the surface with some momentum, as opposed to bubbles that just nucleate within the body of a liquid, like when you open a bottle of soda pop.
First thing you'll notice is that when the tablet is touched to the water, the contact wetting angle forces suck the tablet out from your fingers, and it just envelops the whole tablet. And then you get the chemical reaction starting, and you start to form a whole series of bubbles on the surface of this antacid tablet.
The first time I did this, I had no idea what was going to happen. I had a couple of preconceived ideas, and both of those were wrong. Sometimes you just have to do an experiment in order to figure out what's going to happen.
And these bubbles rapidly grow to a large diameter. So what you rapidly develop a system where you have one or two large bubbles, and they're eating all the other little bubbles. And so the large bubbles are growing even larger, and they tend to push all the small bubbles in between the large bubbles. And they develop this rather stable complex. And here we're going to see Alka-Seltzer, and we're going to see two takes of this just because I find it so interesting. Therefore, you're going to be subjected to seeing it twice. And again, you see lots of bubbles forming. They rapidly coagulate to form two or three major bubbles, and all the little bubbles are pushed in between these big bubbles. And then as the little bubbles start to grow to get a little larger in size, big bubbles swallow up the larger bubbles. So it's a case of the bubble wars here. And you eventually get to a state where you have a bipolar world where you have two large bubbles, and all the little bubbles are pushed in between them in this toroid. And then eventually one of the large bubbles prevails and it eats the other one. And now you have this system where you have one large gas bubble in the center, with this rather thin annular layer, little tiny bubbles all around the outside, and it almost looks like a little planet by the time it grows to that point. And so that's the fate of an effervescent antacid tablet in a weightless environment, which of course is going to be the salvation for zero gravity heartburn for any future space colonists. And I guess you could say that it's a plop plop, fizz fizz, oh what a mess it is. But now that you've ended up, I couldn't resist. But now that you have this system with one large bubble in the center and this annular space of all these little tiny bubbles, now let's see if we can't figure out a way to remove all the gas bubbles and end up back with our sphere of water. So that's what we're going to do here, where we stuck our syringe into this big gas pocket and we sucked out most of the big bubble in the center. And now we give the resultant bubble mixture a little bit of a stir.
And as we've seen in previous Saturday morning science demonstrations, a rotating motion causes the bubbles to go to the center in this tornado-looking core.
Now you can stick in a little cannula and you can suck out the bubbles. And that's what we're seeing here, is various stages of removing the bubbles as they move to the center core of this rotating sphere. And as we do this, the sphere gets clearer and clearer as the bubbles are being removed. And here we see the final stages of removing the gas bubbles that have moved to the core due to the rotational forces set up from having the sphere rotate. And now we are left with basically a sphere of water, almost like it was when we started with. And now we're going to stick a towel up to this sphere and draw the water off, and you'll see capillary action involved with this towel. The forces involved with sucking the water from the sphere onto the towel, and you can see in a weightless environment you have rather large, rather thick sheets of water moving around on the surface of this towel. Something that you don't see if you've got your feet firmly planted on the surface of this planet, where the gravity forces would cause the water to drip off of the towel. In a weightless environment, you'll get these thick layers of water creeping around on the surface of this towel due to capillary forces.
You can have bubbles form from solution, like when you open a bottle of soda pop and the gas that has already been dissolved in solution is just coming out, and that's a homogeneous nucleation problem where the bubbles spontaneously form in the center of the liquid. The water will chemically react with the effervescent antacid tablet and produce bubbles of carbon dioxide gas, and these bubbles will form on the surface of the antacid tablet, and that presents a heterogeneous system.
And you'll see capillary action involved with this towel. The forces involved with sucking the water from the sphere onto the towel.
And Houston Alpha, that's it for our Saturday morning science.